Welcome, everyone. Thanks for bearing with us as we have tech issues at a tech conference. We'll be walking through visualizing or recreating, understanding, and visualizing FiveThirtyEight's elections forecast. And we'll be doing so in two parts. One will be a methodology walkthrough and interactive questions throughout, and then we'll actually dive into a Jupyter notebook and walk through how to create given visualizations within Bokeh. Before all of that, I'll hit you with an agenda here. We'll do introductions, a bit more fully about Matt and myself, and then actually more importantly, to learn about you. We'll talk about how to forecast and how to forecast elections specifically. We'll unveil the secret sauce that isn't so secret of how FiveThirtyEight forecasts elections and talk about best practices of general statistical methodologies in doing so. Then we'll switch over to doing code, and this is entirely open source, creating a dashboard using Bokeh. And lastly, we'll discuss about simulating results and shift over to Q&A. So a full morning, pretty dense, looking forward to what you all think and have to say as we walk through it. So first and foremost, introductions. I'm Joseph Nelson. I care a lot about giving people the skills to use machine learning and data science in whatever profession they work in. On Twitter, I'm Joseph of Iowa. Happily tweet at me or do things like that. Specifically, professionally, I've built a company, taught classes, worked at tech companies. Most recently, built and sold a company called Represently, which operated in the civic technology space. We built a product that made it easier for Congress to process the thousands of inbound messages they receive every week, and sold that relatively recently. I also teach, or at least have taught and continue to consult with General Assembly, which is a 21st century education coding school that teaches classes in software development, data science, product management, UX design, all those quote-unquote in-demand 21st century skills. I sit within the data science vertical. Before that, did some work on the Facebook government politics team. So always been at the intersection of tech and elections and things like that. And so was really, really excited as Matt and I put together this talk. One other thing is that, I hate to say it, but this is actually the second most important talk I'm giving this weekend, as my brother gets married this weekend and apparently I have to do some sort of toast. So we'll see how that all shakes out.
So hello, my name is Matt Brems. Before I move over to the slide where I introduce myself and walk through kind of my background, one thing that I want to call out here that I think is very important is that Joseph, with General Assembly, he taught for 2,000 hours, and you will see why this is relevant in a moment when we move forward to my background. So what I'm particularly passionate about is figuring out how to put the hands of machine learning and data science into others. I'm very, very passionate about education. So went to undergrad in the middle of Indiana, small school named Franklin College. Most people have not heard of it because it's very, very small. I then went to Ohio State for my master's degree in statistics. And while I was at Ohio State, that's where I fell in love with teaching. Specifically, I got to work with the author of Statistics for Dummies. I taught with her and for her, and it was amazing to be able to work with her and see how she communicated statistics. In particular, I was somebody growing up who didn't really understand math. I didn't understand why it was useful. I didn't understand the power behind it, and I wasn't particularly interested in it. And working with her, I was able to help inspire other people to learn what math can do, what statistics can do, and so on. While I was at Ohio State, I also did some work with Smuckers, like the jelly. I interned with them, and really, really importantly, I fell in love with food here. I got to taste test their products, but in my spare time, I built some models and things to help predict where people would buy certain products, what were good test markets for different new products that they wanted to evaluate, and things like that. After wrapping up at Ohio State, I moved to a company called Optimus Consulting. It's a political consulting firm based here in the DMV area. And Optimus Consulting, or while I was there, I was doing data science to work on political campaigns. So we were using models to try and identify who was going to vote, what issues people cared about, and what were the people who knew who they wanted to vote for versus the people who didn't know who they were going to vote for, and then how could we best target those people who didn't yet know who they planned to support in an upcoming election. It's here where I fell in love with FiveThirtyEight and in my spare time built some models. And then I moved over to General Assembly a little bit over 2 years ago. Actually, Joseph recruited me to General Assembly, and that's
Worst decision I've ever made.
Worst decision he ever made. And that's where I fell in love with that confluence of machine learning and data science and education. So the reason that I wanted to call it that Joseph had taught 2,000 hours, it's not a competition, but I've taught over 3,500 hours with General Assembly. He did not know that I put that line in here, but that's okay.
Cool.
It's kind of the relationship that we have. So happy to be here, happy to chat with you all over the next hour and a half about 538 and recreating, visualizing, and understanding their forecasts.
Cool. So I like to joke that those 2 slides are probably the least important in the presentation, which is true, but it was enough for you to be like, oh, maybe these guys could say something that's helpful for us for the rest of the day. We have questions for you. Just raise your hand based on the following prompts, if you will. Gives us the ability to see where the audience sits on some of these key skills and just sort of the proficiency in the background. So raise your hand if you read 538 relatively regularly. Awesome. I'd say about 85%. Raise your hand if you've read 538's electoral forecast methodology. Fair number. Great. I'd say about 15%. Okay. Raise your hand if you've used Pandas, SciPy, NumPy, Bokeh. All right. Maybe about 5% of you use Bokeh. Most of you use Pandas, SciPy, NumPy. Good stuff. And raise your hand if you feel comfortable with descriptive statistics. That is standard deviation, summarization, things like that. Awesome. What about distributions and simulation? What about Bayesian statistics? Inferential statistics? Okay, I'd say roughly about 30 to 40% felt good about each of those things. Great, appreciate that. So today's conversation will walk through each of these things in greater depth. Now, first and foremost, I want to discuss how to forecast, and not just how to forecast elections, but more broadly, how do you go about forecasting anything, which is sort of a bold claim. But we can start with talking about elections in specificity. So if you were to forecast an election, what would you be concerned with? And actually, this is an open question where I want people to shout out answers. What would you be concerned with? Polling. Historical results. Macroeconomy. Voter turnout. Small dollar donations. So fundraising. I think I heard something in the back. Gerrymandering. Okay. Weather the day of the polls. So a turnout factor. Anything else? Okay, we agree with each of those. So if we were to think about each of these factors, you said things along these lines, right? Horse race polls, national mood, presidential sentiment, turnout, geography, demographics, expert opinions, fundraising, social media following, and perhaps more. We even heard other things from the audience. So when it comes to forecasting, of course, the first thing is determining what could be causal in describing the outcomes that we have. One thing that I want to unearth here, in the way that 538 goes about approaching forecasting that should inspire you as well, is that frankly, a lot of what they do isn't the most intense or most unique and novel, cutting-edge, deep neural networks. Instead, it's actually kind of the opposite. It's a very simplistic, straightforward, subject matter informed approach that I think is inspirational for if you want to model any other given outcome. So if we think about modeling broadly, I think we want to zoom out and think about much of the things that we described that predict elections are correct, but the nuances, we could create an infinite number of explanatory factors. You don't have an infinite amount of time. So the nuances, of course, come with how you determine what to include and maybe importantly, what not to include. And so before we continue, we need to ask a bit of a more fundamental question, which is, what is the process of forecasting more broadly? We talked about it in the context of elections, and there's really 5-ish key steps. First, you'd want to think about brainstorming causal variables, as we just did, right? The second thing you'd want to be concerned with is breaking the problem into achievable bits. And that's one thing that we're going to walk through today that is especially key in the way 538 goes about their methodology compared to other things, compared to other ways of modeling and visualizing. They don't just throw everything into a model and say, let's see what sticks, but instead think very deliberately and carefully about each of the independent factors and describing and summarizing those independent factors. Then, of course, you need to collect and clean that given data that you're obtaining. Maybe that's polls, maybe that's fundraising, whatever it is. Once you have that data that's clean and collected, you want to test your results, back tests, see how it performed, in this case, on prior elections, and more broadly on any given situation. And lastly, but perhaps most importantly, frankly, is this idea that except done is better than perfect, especially when it comes to making any given forecast or within the data science realm. It's very common that we as data scientists get obsessive over thinking about every specific small nuance. I've actually adopted a relatively new technique in my own work that I found extremely useful, which is like sprint to get to a model as soon as possible, and then go back and think about the shortcuts you made along the way. What features did you want to clean? What other things did you want to include, omit, shortcuts that you cut? And this gets to a more fundamental concept in statistics, which is our good friend George Box, 20th century statistician, all models are wrong, some are useful. And this idea is just like, it's probably as quippy as a statistician gets of describing that done is better than perfect. Don't let the perfect be the enemy of the good. Any whatever cachet phrase you want to use. Think about being sure that you get to an achieved result before being concerned and hung up on the details. So with that in mind, let's think about specifically the way that we care about elections. So far, we've already brainstormed our causal variables. So the second thing that we need to do is breaking our problem into achievable bits. And from here, now we're going to drift into 538 land and think about how does 538 break all the factors that you described, whether that's polling, fundraising, demographics, turnout, into achievable bits to model an overall election. 538 breaks it up into the following categories: horse race polling, fundamentals, experts, and noise to explain the result of any given election. And this, by the way, is where we will spend the majority of thinking about how do you describe each of these factors and break them down into more discrete, specific bits. So again, this is 538's way of describing elections, not necessarily anything novel from Matt or myself. You may have also noticed, by the way, that we don't work for 538. They don't even know we're doing this. We are just big fanboys that happen to like go really, really deep into what was concerned, and so they decided to give us a stage to talk about that because you all maybe think about 538 in high regard as we do. Okay, so with that in mind, I'm going to say to be continued, if you will, on these portions and really zoom in on breaking the problem into achievable bits. And we'll talk about how that's reproducible across problem space, but we're going to drill into how it's achieved within this specific electoral forecasting stage. So section 2, how 538 forecasts elections and their not-so-secret sauce. So first and foremost, it is top secret stuff here. It is extremely closed form. They haven't posted a methodology. That's absolutely false. Their data is open. The methodology is open. Their historic results are open. And so what Matt and I have done is gone through and picked apart and thought about how this would describe given electoral results. And by the way, the citation is here, and deck is completely open source on our GitHubs if you want to be able to read and dig into this more deeply. Hopefully you feel inspired and empowered by the way that we break it down here, that you feel like, oh, I don't even need to read this thing. I saw what those guys had to say at PyData DC. Nonetheless, let's talk about each of the component parts, okay? This formula is critical to the rest of thinking about how results are forecast in the context of 538. Forecast is a function of polling plus fundamentals plus experts plus some level of noise. That's it, mostly. So thinking about the way that 538 has taken this ambiguous, amorphous, unending problem space and just said, if we brought this into its really disparate pieces, we're going to think about horse race polls and how those trade off. We're going to think about fundamentals, national mood, perhaps there's systemic error if everything pulls in the same direction. We're going to think about expert opinions. And lastly, we're going to think about incorporating noise. Now, it's important to note that 538 has now different levels of their forecast. In the most recent election, you may have seen they had light, classic, and deluxe. And so each of those different levels incorporate different amounts of these independent factors. So for example, in the light forecast is just based on polling, and then of course noise is a part of explaining that result. In the case of the classic forecast, polling and fundamentals are taken into account, and then also noise as a result. In the deluxe version, polling, fundamentals, experts, and noise are all taken into account. And the reason for why there's even a distinction between each of these levels is, I think, gets to two ideas. One, it demonstrates the power of diminishing returns of every additional explanatory factor, frankly. And two, in the context of light is like the polls-only version. If you only thought about polls, and you only thought about sampling and upweighting and downweighting based on a pollster's reputation and time, size of sample, you would get the light forecast. Classic incorporates all 538's mustered energy into creating their best forecast in independence. And then the deluxe version is 538 almost cheating a little bit and saying, okay, these experts over here are also pretty good. How can we steal their results and incorporate them into our own model, right? And so in some ways, the classic is almost like 538's best foot forward, and then deluxe is like 538 plus stealing the knowledge of everyone else in a number of ways. So how do these perform over time? Generally, quite well, as we know. So on election day, the light from, by the way, this is elections from 1998 to 2016. The light model performed 96.2% accuracy, the classic model 96.7%, and the deluxe model 96.9%. And so yes, those hundreds of percentage points better, but demonstrates the diminishing returns of additional explanatory factors. Now, let's drill into polling, okay? So for a while, I've just been up here saying that it's impressive that 538 takes this hairy problem and breaks it into small, really simple bits. What are those simple bits? Drilling into polling a little bit, okay? And the goal here is to basically inspire you to be like, wait a second, this stuff isn't that unapproachable. It just took a lot of time. It took a lot of people thinking and applying deliberate energy to a specific problem space to achieve these results. There's not a lot of magic things happening. I'd argue zero magic things happening. So in the case of polling, we're going to walk through 2 elections in particular and apply the methodology that 538 used to the outcomes of those given elections. Those 2 elections are the Florida Senate, which is actually to be determined. It just now was announced that, well, I guess we knew this was going to happen, to be fair, for a little bit, but this morning confirmed that the machine recount has been finished and hand recount of ballots that have been marked twice or ambiguously or not marked at all are going to be hand recounted by county in Florida. So we're actually talking about an undetermined race in some ways, which is kind of interesting. When Matt and I proposed this talk, we're like, oh, it'll be perfect because everyone will know the election results. We'll be able to criticize and be like, oh, this is where they went right, this is where they went wrong. We're still in it. We don't even know the result of this given election. The second election we're going to walk through in greater depth is Iowa 3. And that's because it is a swingy district that flips seats, and has flipped seats before, and demonstrates a lot of the fundamentals. I'm also from Des Moines. And so that's really, really key to the understanding of why that choice was selected. You're welcome. So in the polling case, this is a sample of the most recent polls in the Florida Senate, okay? And you'll notice there's a number of things here. We have the dates, the pollster, the sample, the weight that 538 assigned it, the result of that poll, the margin, and then these adjustment things on the side. Ignore those adjustment things for a moment, if you will, okay? I want to drill into one specific poll. If you were trying to recreate or build your own electoral forecast, and you're given a bunch of polls, what would you pay attention to and why? So if we look at this, the first poll, and we say, what are the disparate pieces of data that are a part of this thing? First, you have an animated result and keynote. The result, nailed it, which is of course, just the margin between whom won in that one, I guess, was ahead in that sampled audience. And that might be the first thing that we pay maybe most attention to. But there's a number of reasons why you wouldn't pay just attention to the result, right? Because we also care about when was that poll taken, or perhaps who was doing it. So there's other metadata that's useful from this thing. The recency, the size of the sample, the pollster, the institution, the polling institution themselves. Okay, so pause here for a second. We've just taken one single poll, and we've exposed how we can sort of double-click into the things that are more relevant to upsample or downsample one specific data point that's a part of the broader picture. Okay? Now, we could actually drill a little bit deeper, right? We could be author. In the case of 538, when it comes to author, they have gone through and done pollster ratings, which is really going down the rabbit hole. But ultimately, pollster ratings are a function of, given every single time we've seen a given institution provide polling results on an election, let's compare those results to the election's outcome. And then based on over time, we can just compute in its most simple fashion an average of how far that given pollster was from the results of the election. And if you see systemic bias, for example, some pollsters are consistently perhaps +2 Democrat or +2 Republican, you can correct for that. If you see that some pollsters seem to use junk results in some cases, for example, between 2016 and 2018, 538 made the decision to no longer include people that were just casual pollsters like Matt or myself, putting out a Google link and allowing others to answer it. They no longer include that. You must be an official institution governed by what 538 determines to be an official institution. And the point is, this right here, if we paused here, this by itself is its own project, which would be, let's just look at the outcome of polls versus the forecasted result of polls versus the actual electoral results to produce pollster ratings, which then almost rolls back into this broader, bigger mission statement. And this right here embodies the way that FiveThirtyEight approaches forecasting problems and is a great takeaway for I would encourage everyone else that is working on their own forecasting problem in any space to think about things. Break it into discrete bits and thinking about, of those discrete bits, what could you optimize and be more specific about? In the context of polls, that is sort of the lifeblood of an understanding of an election. So it makes sense to devote significant resources and mind share to thinking about how can we improve these generally. Now you could go down the rabbit hole in terms of recency. Do you want to do like an exponential moving average, a weighted average? What's your window size or things like this? You could go down the idea of sample size and thinking about likely voters versus all those polled, which are also weighted accordingly. But the point is, we've taken this one poll, we've exposed that based on this metadata, there's a number of other things that we can care and take into consideration on this single poll. Now zoom back out to all of our polls, okay? What FiveThirtyEight then does is make adjustments based on the factors that we just described, okay? So there's really three key adjustments that they care about. Likely voter, because polls that include likely voters produce different results than those that contain just anyone sampled. Often they bias, or I guess not necessarily bias, but weight towards a more likely Republican result in the case of likely voters. They care about timeliness, in other words, how frequent the poll was selected, and they care about house effects. And the way that they combine together these features, they say they use weights based on an algorithm. And they don't describe what that algorithm is, and they make it seem a little bit black boxy, but I think it'd actually be quite intuitive to walk through what that algorithm could be.
So in looking at this, what you could do is you can obviously fit many different types of models or many different types of algorithms to this. One of the simplest being the idea of a linear regression model or a line of best fit. Just a quick show of hands, how many people are familiar with a line of best fit or a linear regression model? Okay, great. So given that, I don't want to spend too much time discussing that specifically, but what FiveThirtyEight is able to do is they look historically at the gap between certain information, for example, different polls they've gotten in the past, and how far off that has been from, or how much that has influenced the real result. So one big distinction, and Joseph mentioned this earlier, one big distinction in the context of polling is polling registered voters versus likely voters. In thinking about this, when I worked for Optimus, one of the things we did was do work for the Iowa presidential caucuses. And if you think about all of the people who are registered to vote in the state of Iowa versus the people who actually showed up in the caucuses to vote for an individual party, the number of people who showed up to vote was much, much smaller than the entire registered voter universe. And so it's incumbent upon pollsters and political organizations to be able to take that entire universe of registered voters, every person who has filled out their voter registration information, and convert it into a likely voter screen where they can forecast who are the people who are likely to show up to the election. Connecting this with polling, and specifically to FiveThirtyEight, one of the things that you can notice is that if you were to poll all registered voters versus just polling people who are likely to show up, these are two very, very different universes. For example, FiveThirtyEight walks through the fact that their likely voter universe tends to, on average, be a bit more Republican than the entire registered voter universe. And so if there's a poll that talks to all registered voters, FiveThirtyEight wants to administer some type of correction or adjustment to that in order to take that into account and say, well, we know that based on this particular poll in this particular region, we want to shift it a little bit more toward the right or toward the left, depending on kind of the population of people that was sampled. So the way that they go about doing that is they can fit a line of best fit or a linear least squares regression model, where one of the inputs would be what is the result of a registered voter poll. So if I administered this poll to all registered voters, and I've got a huge database of polls from maybe 2000 to 2016, and I say what was that gap between, or how much, or I guess how predictive was the registered voter result of the true final result, I can get an estimate for beta 1 there, which connects that registered voter result to the actual result. We can also add a correction for the amount of time to an election, or how long, what was the window of the poll itself. We can also do that for the pollster bias, which Joseph mentioned earlier. If we look at the average house effects of this individual poll, and we wanted to add an adjustment or subtract some adjustment on the end, we can do that as well. And this is all going to be estimated likely using just a linear regression model, something that by a show of hands, about 95% of the people in the room here were familiar with. So it's a very, very straightforward algorithm that you can use, and it's estimated from past historical data. So 538 obviously has collected a lot of polls over a long time to be able to generate this and estimate to a high degree of precision what is the impact of this pollster bias, or what is the impact of moving from a registered voter screen into a likely voter screen. And we can also add adjustments for things like live calls versus robocalls and so on to try and get a better guess of how predictive those are of the actual end result, that end result being the election in November of whatever year you're trying to forecast.
Now, a good question would be, what if polling is sparse? What if you're in a place where there's just not a lot of data on the ground to determine that we could make these corrections and think about what the margin is, think about, even if you have the most accurate pollsters, if there's very sparse data points, there's only so much you can do. So contrast a highly polled race, like the Florida Senate, with even another competitive House district where Iowa 3, where it did flip, and it actually it flipped even just 4 or 6 years ago. So it's a swingy place, and got a lot of national attention. Even so, it only received 6 meaningful, and I say meaningful because recorded by 538 of the rigorous standards they obtain for pollsters, 6 meaningful poll results throughout the summer and leading into November, right? So we have a very sparse amount of data to be able to say, what is the result of this election going to look like? And not only that, but if you look at some of these results, it is kind of all over the map. You have this Republican plus 15.7 from September 6th to 8th, and then a bunch of other relatively lightly leaning Democratic results. Right? If you just took a weighted average of the margins, you get a fundamentally different picture than if you thought deliberately about maybe some of the timeliness factors or thinking about some of the other areas that we could consider. And so the question of what if polling is sparse, and the answer, and this is where I think there is a fair amount of ingenuity. I mean, a lot of this talk is like 538's not that great as much as we like them. This little bit that I'm about to talk about I think is pretty novel and one that would be useful to reproduce. So sparse polling, they use Cantor, which is a backronym for Congressional Algorithm Using Neighboring Typologies to Optimize Regression. And it's a shout out to the Cantor race where Dave Brad upset Cantor, and people were shocked by it because there was very, very sparse polling in a primary in a relatively heavily Republican district in Virginia years ago. And Cantor's premise is simple. Make a guess of what polling looks like in a given district based on similar districts. Can you approximate what polling would look like in one district if you said this district's mood seems to be most similar to another district's mood? That doesn't seem to be too extraneous of a claim. And so the question becomes, if that's the case, how would you go about determining district similarity and also determining which results you want to incorporate? Really 2 steps. An initial race guesstimate based solely on 538's partisan lean index. In other words, they think about how partisan a given district is based on its historical results. And if you just think about this district is generally plus 6R, and this other district is generally plus 6R, that's the rudimentary guess. Now, how do we adjust that rudimentary baseline? We compare that district to most similar districts, which begs the question of determining most similar districts. And this is the only point in 538's entire methodology where they use something beyond a weighted average, something beyond Bayesian simulation, something beyond a regression, where they use k-nearest neighbors to determine the most similar districts to one another. So adjusting to determine which district is most similar to another district just based on geographic and demographic factors. So Iowa 3 is similar to Michigan 8, which is where Nate Silver is from, and from Iowa, so that's kind of neat. Anyway, so if we look at Iowa 3, in this given case, and we think about more or less similar, I mean, it's relatively intuitive. Places like The coasts are generally less similar, and more similar is upper Midwest places. And so if we think about which districts are most similar to Iowa and the polling results in those districts, now look at the results that we have. Compared to before, where we had that one Republican poll that was plus 15.7, but if we look at the national sentiment in comparable districts, you achieve a result that tells you a very different story about the national mood and sentiment of how things are trending. And this is an example of where polling sort of bleeds into the fundamentals idea that we're about to dip into. But the long story short of the polling section, and we'll look at the polls again for what they predict about our two elections of interest. Long story short of the polling section is polling is the lifeblood of successful electoral forecasting. Devoting significant thought around the credibility of polls, the factors that describe a poll's outcome, and historic comparison of those polls is a high value, probably also high effort task. So it's an area where optimizing and investing and thinking critically and deliberately is a good return on a modeler's or forecaster's time. So if we looked at the polls only forecast about the Florida Senate race, it said roughly D plus 3. If we looked at the polls only for Iowa 3, it said D plus 1.6. Okay? So that's polls only. Now, let's shift to fundamentals. So now we're shifting into the second independent category that 538 cares about in terms of determining the way that a given district or area is going to fall. There's three different types of elections that 538 is forecasting, right? Senate, House, governorships. We've talked mostly about House and Senate so far, and that's going to continue to be the case. But nonetheless, if we thought about the fundamentals, it's many of the things that you all shouted out at us earlier on, or at least 6 of you shouted at us, to be fair. It's 9 a.m. The things that the US House cares about, or factors fundamentals, historic margin of victory, so polls, where do they fall, where do they trend, incumbency polling, generic ballots, fundraising, 538's partisan lean index, where 50% is allocated to the 2016 election, 25% to the 2012 presidential election, and 25% to the state legislative elections, congressional approval ratings, incumbent scandals if relevant, incumbent voting call record, and political experience of the challenger. This order is non-arbitrary. This is the order that 538 states they care about in terms of the relative weights. Now, to be fair, this is an area where it's a little bit murky and a little bit, frankly, frustrating to reverse engineer 538's methodology as they make it relatively opaque about how they weight each of these factors, or perhaps the methodology of what determines a scandal versus doesn't determine a scandal. So it's hard to say exactly what the weight of each of these relative factors are. Nonetheless, the fundamental truth of thinking about and weighting each of these factors matters. So if we compare the US House to the US Senate, it's roughly the same thing with a few changes. The incumbent historic margin of victory matters, I'm not going to say less, but I'm going to say that 538 has better, more deliberate incumbency polling adjustments, or so they claim. So I said roughly that the incumbent historic polling advantage is downsampled and the incumbency polling is upsampled. Everything else relatively the same, except for political experience of the challenger, or more the incumbent, is weighted higher in the case of the Senate. And also, they add a factor, changes in state partisanship, which makes sense. At the Senate, we're talking about a full state. In a given district, we're talking about just that given district. So if we think about the full state and how it's given legislative elections within that state are trending, that gives us pretty good insight about the mood of that given area. Okay, now let's compare governorships to US House. Pretty similar story to the Senate, with one minor change. Incumbent voting call record is not included. So they're not examining the way that the governor used to vote or did vote on given legislation. And the other factors are included all the same. Change in state partisanship, political experience of the challenger, all the same. Now, thinking about what these look like, so one admitted gap in our understanding is understanding the weights specifically of each of these factors. We can see the net output. In other words, 538 makes it clear about how they are upsampling or downsampling a given race based on these factors, but the step between how they produced that weight is not super clear. Nonetheless, we can get a sense of what that looks like based on their transparent methodology here. So for example, if we look at our, it's all good. case you forgot the factors. Yeah, go on. If we look at a given race, the impact score of the fundamentals is demonstrated. So in this given case, the Florida Senate race, if we looked at the fundamentals, you see each of the things that are noted. One thing that I think is interesting to call out here is the challenger experience is extremely high in the case of the Florida Senate race. You have an incumbent who's known statewide and has won previously, challenged by a statewide elected official. Rick Scott used to be the governor of Florida, or I guess still is. And so challenger experience is 8.1 in the Republican challenger's direction, right? Kind of intuitive. So as stated, we see the net output in terms of the way these are shifting and affecting the net result, but we don't know exactly the weights that allowed us to arrive at each of those conclusions. Presumably, if we had to conjecture, it is either or both a weighted average of historic, maybe there's assigned scores of how much incumbency matters, and then regressing those assigned scores versus the outcome and saying, okay, this much roughly matters. Or it could just be a simple weighted average doing the same concept of looking at historically we assigned a incumbent maybe a +5 boost, a +4 boost, and we do a weighted average across and say, okay, on average, an incumbent that's served 2 terms, +4 boost. Nonetheless, that is conjecture at best for what we know. And if we look at the net result of how that affected the prediction for the Florida Senate, we see that it slightly shifts things more democratic overall. The fundamentals are far more democratic given the national mood and some of the other things we saw on the slide. And if we think about this in the context of the Iowa race, very similarly, we have things moving left and right. One thing that is interesting here is the high weight of fundraising that David Young's opponent, Sidney Axney, who won the election, achieved relative to David Young. And it really shifts the election in a blue direction. And so the net result of this race is fundamentals plus 7.1, and we go from 1.6 all the way up to 3.2 in terms of a democratic shift. So the long story short with fundamentals is it is a way to incorporate those other more or less factors that feel intuitive to explain an election's outcome. The fundraising factors, incumbency advantages, things about scandal, state partisanship, sort of like well, without saying fundamentals, of describing fundamentals, the key characteristics of a given race's attributes. Okay? Now the last thing. So remember, the deluxe forecast is 538 sort of cheating and being like, we like our forecast a lot, but we also like these other forecasts a lot too. So how could we co-opt those other forecasts into our own to improve its overall model? And in this given case, incorporating experts is pretty intuitive. Evaluate the historic performance, weight them accordingly, and shift projections. So this is just like saying, is Matt often right or is Matt often wrong? Matt is often wrong, so I should downweight his opinion on things that I do in my own life, right? So the 3 pollsters that 538 cares about are the Cook Political Report, Inside Election, and Sabato's Crystal Ball. And sort of an interesting twist here is how 538 converts their categorical descriptions of races into numeric descriptions of races. Because these 3 are a bit more, I don't know, they're not as precise as 538 in terms of providing numbers. They just provide categories of races. Is it likely? Is it a toss-up? Does it lean? Is it strong? And based on those, 538 has gone back and identified that the average margin of victory when someone says lean or toss-up or so on and so forth maps roughly to these categories. And so we've taken the categorical input and turned it into a numeric input. This is the fancy term feature engineering. But really all it is thinking about if we described some given example and compared it to historic results, what is the threshold by which that result makes sense? And so in doing so, we have the average margin of victory based on those results. We can compare that average margin of victory against the actual election's result and provide a score for the pollsters and themselves, experts themselves rather, and incorporate them into our overall model. And so how does that affect our net result? Well, we've achieved our given electoral outcomes. Now, noise.
Yep.
Go ahead.
So looking back at this previous slide here, what you'll notice is that In the light, classic, and deluxe versions, they care about the polls, and as Joseph mentioned, the fundamentals and the experts version come in the classic and deluxe versions only. But one thing that's present in all three is noise. So it's important to kind of understand this idea of noise and how 538 takes that into account. So to throw back to George Box's quote earlier, we recognize that our forecasts are not going to be perfect. There's a lot of stuff in here, and there's a lot of stuff that's very, very intentional. It's very smart. It is well vested in a lot of subject matter expertise that people have. However, we recognize that despite all of this, our models are still not going to be perfect, but they can be useful. And so we can try and improve our model's performance in the aggregate by quantifying the noise or the uncertainty that exists in all of the polls and the fundamentals and just the things that we haven't been able to control for when trying to make these forecasts. So you can think about the noise broken down into two different components. We've got the component on the left side is within race error, and then the component on the right side is between race correlation, and I want to walk through each of these. So within race error, so what is the error that specifically applies to this one race, whether it's this one congressional district or this one Senate district or this one Senate race or this one gubernatorial race? What is the error within this race alone? And the within race error is a function of the quality of the polls that were done. So remember earlier when we were looking at the polls, there was a weight attached to each of those polls, and higher weights obviously meant that that poll was more important in the final calculation. So we can use that to identify or specifically quantify how good were our polls or how good are our polls in this forecast. The next thing that's considered is the number of polls. There's the number of polls as well as the diversity of those polls or the number of different pollsters that are used. 538 has a strong preference to use multiple pollsters where possible because, as you can imagine, if you only have one pollster who's predicting a certain race, and if that pollster happens to be off in one direction consistently, that's going to be bad. And so that within race error is going to be in part a function of the number of polls and the number of pollsters who are contributing information to this forecast. The last component here, and I'll defer to Joseph to define elasticity because he really loves talking about elasticity of districts, is the elasticity of the district or of the region that is being considered for the election.
So elasticity is the idea of how much one concept responds to some other given concept. Context of prices. For example, when Netflix split out their services from having the online component and the DVD mailed-in component. Maybe you don't remember this. I do very well. The price doubled, and everyone was like, oh man. And actually their stock went tanking at that point because everyone's like, there's no way everyone's going to pay this amount to continue to use Netflix. Wrong. The price elasticity of Netflix is relatively inelastic. Consumers had a high preference to continue to pay and use their service. That is, our demand in response to the price of the good being provided was relatively inflexible. So in the context of elections, what we're thinking about is the elasticity, how responsive a given district's mood is to the national mood. So for example, if a poll comes out that says the president is, I don't know, all of a sudden 15 points unpopular versus 5 points unpopular, how does that affect a given district's mood about the overall race in which they're going to vote? And the interesting thing here is elasticity exists relatively independently of the base number of voters within a given state. So for example, states like Delaware and Rhode Island, which are pretty consistently blue at the statewide level, have extremely elastic voters in terms of people that are willing to respond to national moods. But the base populations of those that are registered to the Democratic Party are just so much greater that the swing in response to that national mood doesn't matter a whole lot. And so when we think about elasticity, particularly at the presidential level, what we most care about is how swingy a place is and if that place can tip one way or another. And that's also the case for a single district or any given Senate seat as well. So for example, in the context of Virginia, Virginia is known as a state that is relatively inelastic in terms of its mood relative to the national presidential polling or things like this. And for that reason, as a battleground state, it's a high turnout dependent state because people are not going to be extremely responsive to, or as comparatively, as responsive to national moods. They already have their opinion relatively made up in comparison to other places. So to win campaigns in Virginia, turnout is generally a higher importance than it is in a place like New Hampshire, where elasticity also is very high relative to a given district. And so you can think about this as a way, again, of almost smoothing across our disparate data points in different polls. So similar to how Cantor thinks about two district similarities, why don't we compare a district to the overall national mood and think about how that matters and how people and voters in that district will respond overall.
So those are the components that focus on within race error. And when you think about the noise that 538 kind of puts into their races, or when they try and simulate races, and we'll talk about this in a minute, or they simulate elections, about 75% of this error, or rather I should say at least 75% of this error or this noise comes from that within race error. However, there's also a non-trivial component called the between race correlation. So this between race correlation recognizes the fact that there are some trends and some things that individual polls might miss, but as a whole, we need to take into account when we're doing forecasts. So 3 examples here. First is a regional or demographic correlation. So perhaps polls or perhaps fundamentals or kind of all of the components that go into the forecast are somehow just they're underestimating a certain group of individuals for whatever reason. So maybe we are underestimating the impact of Latino voters in the upcoming election. Or perhaps we are overestimating the impact of a different group of voters, high-income voters, in the upcoming election. So one example of this would be like the Rust Belt. So if you think about the 2016 presidential election, it was widely believed that Secretary Clinton was going to pretty easily win that presidential election. However, one of the things that sort of influenced the decision was this regional or this demographic correlation. Whereas most organizations treated each state as independent of one another or each race as independent of one another, 538 recognized that there's this between race correlation. So what that means in the context of this example is while voters in each state are independent, given that after the fact, given that we knew that Trump would win Pennsylvania, it was then likelier that Trump would also win Michigan and Wisconsin and states that have similar demographic backgrounds and similar geographic qualities. Whereas what happened with many of the other pollsters and the other polling organizations that forecasted a Clinton victory at 85% or above didn't take into account this between race correlation, and instead they said, well, voters in Pennsylvania are independent of voters in Michigan, are independent of voters in Wisconsin, and so on. And as we know, 2 years after the fact, that's not the case. And Nate Silver writes extensively about this in his 2016 postmortem, describing why 538 was closer than the other pollsters. Another example of between race correlation has to do with incumbency. So, for example, what is the national mood toward Congress? If the national mood toward Congress is terrible, then it's likely that this is something that's going to ripple through all of the elections. And so, if certain elections are skewing in one direction, it's likely that other elections will also skew in that direction. One of the very common tools that pollsters will use is something called the generic congressional ballot. And it is something along the lines of, if the election were held tomorrow, would you vote for the Democrat or the Republican? And this generic congressional ballot does not put in a specific Democrat's name or a specific Republican's name, but it allows us to assess the mood overall of the country. And we can connect that directly to how people are feeling about Congress. If we have a largely Republican Congress and many people say they prefer the Democrat, or we notice a shift toward the Democrat over the past 6 months, that is a good indicator that perhaps people are not pleased with Congress and the job that they're doing. So related to that, this between race correlation, incumbency has an effect specifically among incumbents. If incumbents across the board are performing poorly, then you take another race where there's an incumbent. Even if we don't have as much polling, they're probably going to perform worse as well. Or if incumbents across the board underperform their polls, the same is likely to happen to other incumbents, even if we haven't actually observed them specifically underperforming their polls. And then finally, the last example here is a national swing. So maybe there's just this systematic polling error. Maybe, and sort of connecting this to the regional and demographic correlation, maybe there's a specific group that was just undersampled. For example, if you think about the 2008 election, I talked earlier about identifying a likely voter screen. Likely voters versus registered voters. Likely voters are often defined based on who showed up in past elections. If you think about the 2008 presidential election, if you're going to define your likely voters based on the people who showed up in 2004 and 2000 and 1996, you're going to dramatically underestimate the proportion of the electorate that is African American. Because in 2008, then Senator Obama was running for president, and we noticed an enormous surge in people of color turning out to vote. Similarly, thinking about the 2016 Democratic presidential primary, we see an enormous surge in the number of young people and the proportion of young people getting out and voting, most specifically for Senator Sanders. And so based on that, we can recognize that sometimes there is this systematic polling error. When we base things on the past, it's really difficult to forecast things in the future when there are intangible things that we might not be able to quantify. It's difficult to quantify the effect of Senator Obama on people of color and the proportion of the electorate that is people of color based on when we haven't had an election yet, when we have no data to support that beyond polls. And so there is often this example of a systematic polling error that just affects all of the races in the country or all races in a particular region of the country. So 538 accounts for this noise. Again, there's this within race error that's specific to that race, and that makes up at least 3/4 of the noise. But then there's also this important component that makes up 1/4 of the noise, and that's going to be the between race correlation. So what we want to do now is we want to move over to the code that we have. So we've got 2 Jupyter notebooks. You're welcome to follow along if you'd like. We'll obviously have it up on our screen and I'll walk through the code. But if you would like to follow along, please feel free to go to this link and I'll keep it up here for a moment. bit.ly/PyData DC 18-code. And I'll give you 10 or 15 seconds to jot that down. While people are jotting that down, are there any questions that you have before we shift over to those notebooks? Okay, cool. Give you another couple of seconds. Okay. So if you go to this link, what we'll do is you'll notice that we've got this set up, and there should be 2.
Can you verify that? Can someone raise your hand if you were successfully navigated? Cool, great.
I think it should be HTTPS.
Awesome. So,
HTTPS.
Yeah.
Okay, so somebody in the audience says that you need to go to HTTPS. Please add an S after the HTTP here.
thank you.
Joseph did that slide.
Matt didn't check it.
When did you finish that slide?
Hey, you.
So you'll notice that we're on Joseph's GitHub. Again, Joseph of Iowa. He has a tattoo of Iowa on him. It's ridiculous.
It's not true.
He loves Iowa and everything about it. It's a little weird. But so we've got in the repo here, we've got PyData DC 2018. We've got 2 IPython notebooks that we're going to go through, so feel free to fork and clone this down if you would like to follow along. We have Bayes walkthrough and Senate dashboard. And what I'm going to do is I'm first going to go through the Bayes walkthrough, talking through what is Bayesian methodology at a very, very high level. We'll go through a couple of examples. We'll wrap that up with how we turn Bayesian methods and the understanding of a particular parameter of interest into election results. And then what we're going to do is we're going to walk through how you can set up your own Senate dashboard in Bokeh and how you can export it to HTML so that you can host it on a static site if you would like to do so.
If you've not used Bokeh, I recommend Conda installing it.
Okay, people in the top tier, are you able to see this?
Yep.
Okay, thank you. So what I'm going to do is I'm going to very quickly walk through Bayesian statistics. I know Joseph asked about this earlier, but we've had a decent number of people join since we started. So quick show of hands, how many people are comfortable with Bayesian methods or Bayesian statistics? Okay, so about 25% of people. I saw a couple of so-sos. So we're going to quickly recap this. So the idea behind Bayesian statistics, and you'll see why this is relevant in a minute, but Bayesian statistics is a branch of statistics that will allow us to directly estimate some parameter of interest with a distribution. So if you think about a traditional statistics class where you learn about things like hypothesis tests and confidence intervals, you might have heard the term frequentist statistics. That relies on a certain interpretation of probability, and you treat those parameters as having one value. So, for example, the parameter of interest we're going to talk about is the proportion of votes, or the percentage of votes that the Democrat is going to get. I'm going to call this P sub D, or PD. And if you were to generate confidence intervals or do a frequentist hypothesis test, you interpret PD as just some fixed value. So you might say that the Democrat will get 53% of the vote, and that's it. Whereas with Bayesian statistics and Bayesian methods, instead of saying there's this one value, we can actually put a distribution or a range of values around it. And it's different from a confidence interval for a couple of reasons that I'm going to gloss over in the interest of time. But what we can do with Bayesian methods is we can actually say that 53% is our likeliest value, but you can imagine putting a bell curve or really any distribution over this that allows us to say that the Democrat it's reasonable that the Democrat wins between 48% and 58% of the vote. And then we want to be able to translate these distributions into electoral results. We can do so through simulations. The other kind of big benefit of using Bayesian inference or Bayesian methods is that we're able to combine two things together. We can combine our data, and the term we're going to use for this is our likelihood, with our prior beliefs. When you're doing frequentist statistics, or the classical statistics that you might have learned in undergrad or in high school if you took like AP Stats, if you go ahead and do frequentist statistics, the only thing that you have is the data. You let the data speak for itself. But the way that science and knowledge work is that we recognize that there are certain values that something might take on. For example, depending on the Senate race you're talking about or the congressional race you're talking about, maybe we know that it is all but impossible for a certain person to receive 80% or 90% or 100% of the vote. So instead we want to say our prior beliefs fit this certain kind of model. And so Bayesian inference is going to allow us to summarize our prior beliefs and our data and combine them together so that we can get, hopefully, a more informed and a better result. So 4 terms that I'm going to use here. Distribution, I've already described this a little bit, but a distribution is the set of all possible values of a variable and how frequently we observe each of those values. So in the context of PD, again, PD is the percent of votes that the Democrat is going to get in the upcoming election. So the distribution for PD will be the set of all possible percentages of votes that the Democrat can get and how frequently we would see each of them. You can visualize that intuitively like a histogram or a bar chart. Our prior distribution is the distribution that you and I come up with that say, what are our prior beliefs or what is our prior understanding about PD, that percent of votes that the Democrat is going to get. Our likelihood is how the data summarize that parameter of interest. It's how the data summarize PD. And then the posterior distribution is going to rely on some math that's going to take the prior beliefs that we have and our data and combine them together. So intuitively, I like to think about the posterior distribution as a compromise between that prior distribution and the likelihood that we generate. And so what I've done is I've explained these terms, but I want to put some code to this and actually show what this means. So go ahead and import these packages, and you'll be able to run the entire notebook if you'd like. But in putting this into action, I want to be able to generate some data through NumPy. I want to be able to plot and visualize this together. So let's say that I live in a district where I really, really strongly believe that the Democrat is going to lose badly. So then what I want to do is, without seeing any data or without taking any polls, I want a prior distribution that matches those beliefs. It's common for us to use a beta distribution when we model probabilities. The beta distribution is a distribution that is continuous between 0 and 1, and that's it. So if you're talking about probabilities, which can take on any number in between 0 and 1, this is a common thing for us to do. So there are two numbers that we have to specify if we want to use that distribution. They are called, in this case, they are called A and B. So I've already filled in this code for you. But if I think the Democrat is going to lose badly, I set A to be 10 and B to equal 40. I'm glossing over the details of how I picked those. But if you run this cell, you can see this distribution. So on the horizontal axis, these are all of the possible values of PD, the proportion of votes that the Democrat is going to get. On the vertical axis, we have the density. So we have kind of the probability or the likelihood of each individual value, which gets a little weird to talk about for continuous distributions. But in this case, I picked my values, here it's alpha and beta, but I picked these hyperparameters specifically because I think the Democrat is going to do really badly. So if we look at this, almost all of the weight in my distribution based on my previous beliefs about how the Democrat is going to do is between about 10% and 30 or 35%. So this is an example of coming up with a prior distribution for our parameter. In many cases, this involves subject matter expertise and an understanding of these probability distributions. To show a different example, let's say that I think the Democrat will win, but I'm not very certain about that. So visually, before we even run this, if you think about how I can shift this blue distribution here, if I think the Democrat's going to win, but I'm not as certain, you can imagine taking this distribution, pushing it over to the right-hand side, where the proportion of votes the Democrat gets is probably going to be greater than 50%, but not all of the weight of that distribution will be beyond that. So I pick alpha and beta to be 7 and 5. And we get this distribution. So the likeliest value for PD is around 60%. It's actually at exactly 7 divided by 12. But we see a much broader spread because we're less certain about what's going to happen. The last example, let's say that I just moved to a district and I literally know nothing about either candidate. In this case, I want a prior distribution that reflects that idea. I'm not going to put my finger on the scale. I'm not going to discuss or try and influence things in any way. And I want a prior distribution that reflects those beliefs. I set my alpha and beta parameters to be equal to 1. And so then my distribution is this very boring flat line in between 0 and 1. So we can come up with a range of prior beliefs that goes from completely uninformative to something that is much more specific if we have informed previous beliefs. So that's our prior. Now, how do I connect this with my data? In this case, I'm going to talk about data in terms of polling. So remember that our posterior distribution is a combination of our prior and our data. So we have to figure out how does that data or how does that likelihood come into play. The likelihood function should be a reasonable model for how that data is generated. So if I administer a survey to n different people and I say, do you plan to support the Democratic candidate in the upcoming election? A reasonable model counting up how many people say yes is the binomial distribution. What we're doing here is you can think of these as n fixed trials with a certain probability of success. There are only two outcomes, success and failure. In this case, I'll say success is voting for the Democrat. Failure is not voting for the Democrat. And I just mean that in terms of like actual statistical terminology, not no personal opinions here. Although
we've been so non-political until now, Matt.
Sorry. Well, they saw my Twitter handle. So if you go to my Twitter, it's been political recently. But so we've got n fixed trials. We have two possible outcomes, the Democrat or not the Democrat. And we can treat these trials as independent. Or if I assume that I sampled these individuals from a random sample or a true random sample, then I can assume that these observations are independent of one another, which matches all the assumptions you would need for the binomial distribution. It's just a convenient way for us to count up how many successes we observed out of a fixed number of independent trials.
Hey, Matt, what's a binomial distribution?
What? What's a binomial distribution?
I'm asking you to review binomial distribution.
Oh, so a binomial distribution is going to be a distribution that can model exactly that. So specifically here, what I want to say is, let's say that I were to survey 40 different people, and 30 of them say they plan to support the Democrat. The binomial distribution is a very, very convenient distribution to say, how likely is it out of 40 people that I get one person to support the Democrat, or 2 people, or 3 people, or 4 people, and so on. So this binomial distribution is going to be a good way to model exactly that.
Thanks.
So let's say that I administer a survey, and I get responses from 40 people, and 30 of them say that they plan to support the Democrat. If you run this cell, this is what that binomial likelihood will look like. This is saying, how likely is it that my probability of success, or the proportion of people who vote for my Democrats, are each of these values given the data that I observed? So here, if I observed 30 people who said they're going to vote for the Democrat out of 40 total individuals, it makes sense that the peak of this distribution, 30 over 40, is right around 75%. In fact, it's exactly 75%. And so this is the binomial likelihood based on the binomial distribution, which models how likely is it that we observe different probabilities of success given the data that we observe from our survey. One note that I want to make is the likelihood here is not dependent on our prior. These are totally independent of one another. I came up with my prior distribution or my prior beliefs before looking at any data or before administering a survey. Now my likelihood is where my survey data comes in or my polls come into play. So let's say that instead of doing a survey of 40 people and getting 30 responses in support of the Democrat, I sample 400 people and I get 300 people who say they'll support the Democrat. Well, we still expect there to be a peak right around 75% because we've got 300 successes out of 400 trials. 3 over 4 is 75%. But we're much more certain that that distribution is going to be very, very close to 75% because my sample size is larger. This seems to make sense. If you have a sample size of 10 versus a sample size of 1 million, and you get 8 out of 10 or 800,000 out of 1 million people who support somebody, there's way more certainty in this 800,000 out of 1 million people, to take this to logical extremes. So in this case, as that sample size increases, the certainty of that likelihood becomes more certain, or that distribution becomes narrower. So to look at a prior and a likelihood together, let's say that I use this situation where I think the Democrat will win, but I'm not very certain. So my prior distribution, I'm going to pick a beta 7.5. And suppose I administer a survey to 400 people and 300 of them support the Democrat. In this case, I'll use my binomial 400 trials with 300 successes as that likelihood. And this visually is what we get. So in orange, the big, nice-looking bell curve, that is our prior distribution. And our prior distribution is centered at about 58 or 59%, exactly 7 divided by 12. But there's a lot of spread under that prior distribution. For the likelihood distribution, you'll notice that the green line representing the mean of that distribution is at 75%, because again, we saw that 75% of our people said yes, they'll support the Democrat in that poll. Now, the reason that the likelihood looks smaller is that the likelihood here is, and I'm going to gloss over this, technically not a distribution. So it's not going to integrate to 1, or the area under the curve isn't going to add up to 100%. And so because of that, that's why the distribution looks a lot smaller. It's not going to affect any of the work we're doing, but just something to keep in mind. So the important points here are to look at those vertical lines. So the orange line represents the mean of our prior beliefs. The green line represents the mean of our likelihood, or the likeliest likelihood value. So based on this, if you think about what is going to happen to our posterior mean, or when we combine our prior beliefs and our data together, that posterior mean should fall somewhere in the middle of the orange and the green lines. And that's because the posterior distribution is a compromise between our data and our prior beliefs. So I've written a function here that will allow us to plot the distributions together, and we can just pass in what do we think our beta distribution parameters will be, and then what do we think our binomial likelihood parameters are going to be. So let's say that, again, I think the Democrat's going to win, but I'm not very certain about that. And I survey 40 people, and I get 30 positive responses from that. If I model these, I'm looking at my prior and my likelihood, which give me that posterior distribution. And in this case, that posterior distribution looks like it's a compromise or somewhat in between my likelihood and my prior. But in this case, the mean is closer to my likelihood, which means my likelihood is providing stronger evidence here. Because remember, my prior beliefs, I wasn't very certain about it. So the posterior more closely matches that likelihood. Similarly, we can run an example here where I thought the Democrat was going to perform really, really badly, but we run a poll and the Democrat gets 55% support out of 100 people. And we can visualize these distributions as well. So again, the important thing is to look at the means of those distributions. And in this case, we also see that the blue posterior mean is this compromise between our prior beliefs and the survey data or the actual data we have observed. Putting this all together, this is under the hood what FiveThirtyEight does. And what they do is they use this to turn this into election predictions. So let's say that I have that posterior distribution and I pull one value from the posterior distribution. Remember, my posterior distribution tells me what is the probability of support, what is the percentage of votes the Democrat's going to get. Well, if I pull one value from that posterior distribution and the Democrat gets more than 50% of the votes, just assuming that there's two people in the race and getting 50% means you win, I'm going to call that a win for the Democrat. If I do this for 100,000 different elections or get 100,000 different values from the posterior distribution, I can then, in effect, simulate 100,000 theoretical elections. If I simulated 100,000 elections and the Democrat ended up winning about 60,000 of those 100,000, I'm going to estimate that the Democrat has a 60% chance of winning the upcoming election. So we can run this here in a quick example. If I have a beta 7.5, that's where I think the Democrat is going to win, but I'm not certain, and I poll 40 people and 30 people say they're going to support the Democrat, I can generate 100,000 observations from the posterior distribution here. I'm calling that PD. If I plot this histogram here, this describes my posterior distribution of PD, where PD is the percent of votes I think the Democrat is going to get. So out of 100,000 trials, we can see that on average, the Democrat seems to get about 70% of the votes, and in almost all of the cases, the Democrat is getting more than 50% of the votes here. I can then convert this into elections by literally going through every value in the simulated distribution and say, well, let's call this a win if they had higher than 50%. And we can check out that mean. If we look here, based on that data we sampled, the Democrat has a 99.925% chance of winning based on that posterior distribution, which combined our poll and our prior beliefs. So specifically, what FiveThirtyEight is going to do is they're going to use a more sophisticated method of combining all of their polls together and bringing in more noise. But they're going to get a distribution of values, this posterior distribution of values for each of their races Then they can simulate one race across each of the possible Senate races and say, the Democrats won 26 seats in this out of the 35 that were available in this election. And then we can do the same thing again over and over and over and over again to get a better understanding of how this is going to go and get a probability estimate for how likely is it that an individual senator wins their seat, or an individual governor wins their seat, or an individual party wins control of the House of Representatives or the Senate. So all put together in one cell. You can see this in a different example where, in this case, it's far less likely that the Democrat is going to win, and we estimate that at about 5%. The last thing I want to do is let's shift over to the other notebook and look at let's look at how we can take this and build it out in Bokeh together and what a dashboard looks like. So I'm going to open up the Senate dashboard IPython notebook, or Jupyter notebook, I should say. Up here, we have a lot of imports. We're going to generate a map, we're going to generate a histogram, and we're going to generate options for this, so that if we wanted to look at the light versus classic versus deluxe, we could do that. The function that we've got here is going to set up a radio button to say, do we want the light, do we want the classic, do we want the deluxe forecast? So, acknowledging this up front, this button is there for show and will not actually change results. However, we can then set up our map for our forecast, and we can use Bokeh to do this. So Bokeh has a built-in set of values for all of the states. We can unpack all of the states, and one of the nice features of Bokeh as a package is it will generate interactive visualizations, so we can determine certain tools that we want to exist here, and we're going to see these in a moment. So I'll run this function run this cell to create map results. I'm going to just simulate how many Senate seats are won by the Democrats. I'm just pulling this from a distribution rather than bringing in a bunch of 538 data, which will take more than the 5 minutes that we have left. And similarly, I've set up a histogram here, where this histogram is also going to be interactive. You'll notice that there's tools in here as well. You'll see something called a tooltip. We'll be able to visualize this in a moment. And then this is where all of those pieces will be pulled together. So if you want to generate a Bokeh dashboard, this is how you would do it. You can define a function for each of the things that you would like to do. And then they have a function called grid plot that will allow you to organize all of these together. So in my top row, I'm just going to have the options or the buttons for the light, classic, and deluxe forecast. And then in the row beneath that, I'm going to have my histogram on one side, and my histogram is going to show the simulations that I just generated. And then on the right-hand side, I'm going to have the map of the United States, bringing in the states data that Bokeh has loaded up. And if I want to generate this dashboard and open it in a notebook, I run these two functions. Output notebook is going to, unsurprisingly, output this data in the notebook. And then show is actually going to pull it up. So what we see here is, again, there's those radio buttons up top for light, classic, and deluxe. We have, and I'll zoom out a little bit, forecasting the race for Senate. So on the left-hand side, we have the number of Democratic Senate seats, and we can move over to a map of the United States. And as you mouse over, I'll zoom in so that we can see this. There is this thing called a tooltip that we have defined to be able to report, as you mouse over a bar, what is the number of Democratic seats that somebody won. So here we've got 45 seats, 46 seats, 47 seats. You'll notice that once the Democrats control the majority of the seats, that the bars turn to blue. And then over here, we have a map of the United States, which similarly is interactive. So you'll be able to zoom in here, but we can look at Iowa, or we can look at Kansas, or we can look at Indiana, and the tooltip here shows what is the name of that state, as well as the probability of a Democratic win in that state.
To be clear, these are arbitrary values for this.
Yes, these are arbitrary values in here. Although better than some of the things we saw. The first time that I showed this to Joseph, he's like, why is Texas so blue? It's only light blue here, but. So what you might want to do though is say, Jupyter notebooks are nice, they're helpful tools, but beyond this, what we want to do is we actually want to take these tools, we want to deploy them somewhere. Well, Bokeh has a convenient way for you to do that as well. You can generate an HTML file. So using the output file, you can just send this to an output, add an HTML suffix to it so that it will automatically render in a browser window for you so that you can look at this outside your Jupyter notebook. Additionally, if you, one of the other things with this is, I'm going to click back to the Jupyter notebook for a moment. As you generate this output file, if you look back in your folder, there is now a folder called output HTML there. So you can take that dashboard, save it as an HTML file, and then once you've saved that as an HTML file, you can attach that or load that onto any static site of your choosing so that you can have this interactive dashboard available on a personal website. Not limited to 538 forecasts, but this is a convenient way to leverage that Bokeh library to do something interactive. It's built on top of JavaScript. It is a flexible library for visualizations of the interactive type. So with that.
Yeah, so we are running shy on time, so a few things. One is that Matt and I are happy to hang out for questions because we robbed you of the Q&A time at this exact time. Second thing is high-level notes to comment and leave you with some parting thoughts. First thing is the importance of breaking seemingly big, hairy problems into discrete, smaller ones and focusing your time where there's going to be the biggest value in terms of, in this given case, your forecasts, output, and accuracy. The second thing, and something that I want to chime in on our Bayesian statistics discussion, is sort of like a little anecdotal note and then hopefully something inspirational if you've never used Bayesian stats before, is this idea that when I first encountered Bayesian statistics, I remember someone telling me that they were able to summarize the world with like a single data point. And I was like, that's not true. You don't know what the world looks like with a single data point. You need at least two for an average or something, right? And Bayesian statistics introduces this world where you could think about, as Matt described, identifying a prior, and then seeing how that prior would change relative to a single piece of evidence to produce some posterior distribution. And that way of thinking in terms of distributions and in probabilistic instead of single point estimates is incredibly powerful, as you can see for what it unlocks for us. The last thing is that this code is entirely open source, including both the Bayesian walkthrough, the deck, and the Bokeh dashboard. The Bokeh dashboard is purely exemplary, as Matt described, and something that you should use as a reference as you continue to think about building things like this. So hopefully you've taken away an ability, at least at a minimum, an appreciation of breaking down methodologies, and at a maximum, a strong understanding of Bayesian statistics, how 538 thinks about things, and a little bit more about Bokeh. So with that in mind, I want to thank you all for coming out at 9 a.m. on a Friday and listening to Matt and I talk about stats for way too long, and welcome you if there's questions to come, hang out and chime and throw tomatoes and that type of thing. So thanks so much. What do you want us to do now?
We got mics. You guys want to use them?
Oh, for Q&A?
Yeah.
Sure, all right. Well, we need the Q's. We'll try with the A.
Hi, this was really great. I just wondered if you could maybe contrast making dashboards in Bokeh with maybe other tools. Like I'm thinking about Plotly Dash. I don't know if you've ever used that.
Yeah. Go ahead.
So I personally have never used Plotly Dash or really any other dashboard generation software. The reason that I specifically like this is there's a couple of reasons why I like it. I find it to be relatively easy to deal with. It plays nicely within the Python. It's very easy to export things. It does have the interactive tooltips, which I particularly appreciate. And I think the gallery online and the examples that they have are very, very helpful in getting that done. That's not to say that there aren't examples for Plotly and Dash and the like, but that's my personal experience with it, is that given my experience with Python, which is, I think, limited, I think that it's a relatively easy way to get started with the dashboard if you're comfortable with Python.
I was just going to provide a quick, so we only described bokeh in this single example, which is one tiny piece of the overall interactive visualization. Of course, within Python land, there's hollow views. There's, as you described, Plotly. I like using Folium for maps. There's a high array of different libraries that you could choose and use within Python. Specifically why bokeh, Plotly, et cetera are quite strong is you don't really have to know JavaScript to make interactive things, which is really quite neat for us folks that are not great at JavaScript. Broadly speaking, though, in terms of making dashboards, I don't think you should limit yourself to frankly needing to have Python. Of course, there's like great tools like Tableau, where it's just a greater amount of accessibility based on someone's background. But broadly speaking, bokeh is a great tool to marry if you want to do some level of modeling and forecasting within Python. All the data is already in Python, so why not export it and make it easy for your teams to be able to view it in Python as well.
You specifically talked about, I think it was like in the noise model, like changes in demographic turnouts and stuff like that. And then I think it was in another factor like scandals and stuff like that. As someone who followed 538's presidential forecast related to Donald Trump, and I think you mentioned this, that like Washington Post or some other people were like 0% chance of winning. Like I was following it right up until the election, saw it jump to like 33%, was like, what's going on? There was the James Comey scandal, like various things like that. Was that reflected in polling data, or was that like other, like the other features that you mentioned in their poll, like scandals, like them sensing some kind of different demographic turnout, et cetera?
Yeah, so I think that's a really good point to bring up, and that is while we treat each of these features as independent of one another, while we look at polling independent of the fundamentals, independent of and so on, one of the things that I think is important is that information is going to come in a lot of different avenues here. So as an example, it is possible that what they did was, at 5:30, it was maybe they added a scandal component to Secretary Clinton. I would imagine, given emails in Benghazi and like just the news following all of that there was already some component of that there. That being said, they might have tweaked that to make that larger. That's something that was additionally represented in polls. And so if you look at polls before, it was like 11 days before or whatever, she was doing substantially better. After that point, there was a dramatic drop. Related to that, that's something that you see all throughout the 538 forecasts. For example, one of the components that Joseph talked about was the experts. They literally take an average of the experts' weights or the experts' ratings and combine those together. And they feel that, or Nate Silver wrote in his methodology article, that what the experts do is really good at picking up on these micro-level trends that other people haven't yet picked up on. And so it's a leading indicator in that sense. However, it is also often a lagging indicator of other things. And so, for example, if there's the congressional ballot that starts heading in a certain direction, or if there is economic evidence to support a certain candidate or something like that, what will ultimately end up happening is that the 538 noticed that the experts' ratings will not just be independent of that and just focus on those micro level things, but will also be influenced by other things that they're already bringing into their model. All this is to say is that a lot of this is going to be very complex, and there's going to be an individual piece of data that might influence things in multiple situations, whether it's in changing demographic trends, whether it's in scandals, whether it's in experts' ratings, or so on.
We knew the question in 2016 would come up, and that could be its own 90-minute thing in terms of what 538 messed up. I'd condense it to like really 3 key things. The first is that the polls are relatively well done, actually, in terms of predicting the way that individual places would vote. It was simply the incorporation of who was polled properly in terms of a number of swing states. The second is, as Matt described, systemic factors in terms of when given, for example, if you knew Pennsylvania would go one way, that would say things about Ohio and Michigan as well. And the third thing is that 538 called out the fact of sparse polling in areas where they wish they had more. Michigan's a good example of that. So if you had to condense it down to three things, it's polling the right audiences, systemic error across polls, and the need to have richer data across all regions.
Also Russia.
For a presentation, I could follow this and adapt it, but if you were, I would imagine this is all in a pipeline going all day, 365. And would you change any choices in things such as Bayesian versus more classical techniques? Well, that's other approaches for performance, for the fact that you might be doing your earlier discussion, K nearest neighbor. Can you just do that once and then incrementally change things, or do you have to start over every iteration?
So the question is about, we described a number of smaller bits that went into the overall methodology.
Yes.
The question is, if you edited any of those individual bits, how would that affect the other components?
And over time, if you're going to do this on massive scale, and repeatedly, would that change your choices at all in some of the statistical approaches you've used?
Yeah, so I think you bring up a really actually good question that faces a lot of statistical modeling, so I can take it out of the context of elections for a second, then bring it back in. So for example, asset managers have this problem where they do a really good job of identifying, at least the top ones, assets that are correlated and creating portfolios that de-risk and assume some amount of risk. And let's say they take a bunch of new funds and new investment and they want to manage an additional number of people's money. They can't simply just buy an additional amount of assets of the existing strategy that they want to use, because there's a limited amount of liquidity, things are correlated in different ways, and you can't just take this and multiply it by 10. So the question of, if you have a strategy that you relatively like built up of individual component parts, how do you adjust and scale that strategy is not unique to just elections. In the context of elections, there's, I think, I would describe two things that I'd be really cognizant of. In this context, there's a lot of systemic error that could cause one given technique to affect every other technique across the board. So for example, Cantor is an example where it is in contrast to many of the cross-race polling factors that Matt described in noise. Cantor is actually the antithesis of that. It's like, why don't we try to make two districts that are different, look similar to one another, and actually correlate them? Whereas at the same time, de-risking some amount of the noise says, let's not assume that places could not have systemic error across them. And so in other words, if you changed a factor that affects multiple parts of your overall forecast, I think that's an area where you're going to be performing near heart surgery in terms of editing a component. There's other factors, however, where I don't think that's the case. Pollster ratings is a good example of something that you could do in independence and siphon off of the other parts of the aggregation and forecasting that you're doing. Ultimately, and then the second part of your question was around how often do you like rerun and retune and retrain? And do you do it entirely? Which I think is extremely, like most things, context specific. In the context of 538 and pollster ratings, I actually don't know how often they redo it, but that's not relevant to the point of my answer, which is that you don't need to redo the pollster rating every single time a poll comes out. If I had to estimate, I would estimate that 538 redoes their pollster ratings after each election at most, right? And then reruns that model and says these are the new scores for which we believe a given pollster is going to output. So the timeliness of updating a given model's output is dependent upon how just in time the results need to be. And you described KNN. I would presume, without knowing, of course, factually, that they ran the KNN model once to say these demographics are demographically similar, or excuse me, these geographies are demographically similar. That's enough and sufficient to use this for 2018 going forward. Maybe they will rerun that for 2020. But long story short, how often you update a given component of your model is extremely dependent upon what the purpose of that thing is. Like, contrast that with Netflix real quick. Their recommendation algorithm updates all the time, and in fact is at least multiple times per day across user actions because they have so many, and that dictates how many people are going to spend time on site and things like that, which updating the recommendation algorithm needs to happen much more frequently compared to updating, say, KNN, for which states are most similar in the context of 538.
And really quickly, just so as I mentioned at the beginning, my background prior to General Assembly is working in politics and political consulting. And so one of the things that we did was we had set up a series of tools that would allow us to much more efficiently do our work. For example, we weren't doing the same stuff that 538 was doing, but understandably, Nate Silver is not actually sitting at a whiteboard and redoing this every day and updating their predictions. And there's tools and pipelines that exist for that. The reason that I bring that up is that we did something similar in the context of actually trying to model with our data in this very efficient way, because we knew what the data was going to look like, we knew what the output was supposed to look like, and so on. And with that, we would update it after every election cycle, and there are two main reasons for that. The first reason is that you only get approximately, aside from early voting and absentee ballots and all that, 1 day of voting or 1 day of data. So you've got election day, but that's really it. So in terms of, if you think about classical machine learning where you do training and testing sets and you evaluate your model on your testing set, it's really hard to evaluate your model on and your processes more broadly on unseen data, just because, well, until November 6th or November 8th or whatever happens, you don't have that actual data. So that's one thing. The other thing is that as you try and make major changes during the election, there aren't just the inevitable bugs that will come into play, and you don't want anything to be down, but the other thing is you then run the risk of putting your finger on the scale too much, because you say, for example, let's say that 538, after Comey made his announcement, said, wait, Clinton's too high, we need to relook at this. And so they start tweaking things in order to get the result that they expected to get, rather than saying, let's trust the process, let's let our model and this infrastructure we've built up kind of suss that out, and let's let the public determine that rather than us. So I would agree with Joseph that they probably are doing major updates and tunes to these after every major election.
Thanks for the presentation. You actually bring up the question I want to ask. It's about the model evaluation. I believe that you have a handful of models in hand, but you just show a chart about your in-sample evaluation, but that is in-sample. It's like the noise will make up about 94%. That would bring up the concern of overfitting. So in economic forecasting, we are concerned with forecast mean square error, or the other evaluation stuff. But you didn't show in the presentation. I'm just curious about how you choose the final model.
Yeah, so in the context of trying to forecast when you don't actually have that real data, you don't have valid data on which to evaluate, you have to do what we do all too frequently in data science, and you've got to make assumptions, and you've got to just use the data that you have. So that data that you have can come in many different forms. If you're thinking about the day or the week before the election, you can often get early voting and absentee ballot numbers, which those are updated daily by individual secretaries of state across the United States. And you can use that information to try and identify within a week of the election or within a month of the election how your stuff is tracking relative to what you expect. That being said, more broadly, you're absolutely right. There's this enormous concern. How can I forecast what the election is going to look like in 2016 when we don't have that information? So you rely on absentee ballots and early voting. You can rely on primary elections if you have that. But to be perfectly honest, you just try and set up proxy variables and hope they're good enough. You might say, I'm going to define a like election. So an election that's like 2016 is probably 2012 or 2008. And so maybe you use both of them together or each of them independently as a stand-in for your Y variable or as the 2016 presidential election. But even with that, there's not a good answer to that, because optimally we want that data, but we just don't have it. So we have to essentially create data or use data that exists, as bad though it may be.
I think one thing to note is that's actually one of the key value adds of Bayesian modeling, is you can compare the limited amount of evidence that you have compared to what your beliefs about a given system may be. So in the context of 538, they actually have a Bayesian model that estimates how election day is going to look based on national mood and based on comparable elections, so 2014 for 2018 because it's midterm years. And as we approach election day, the weight that that Bayesian prior receives relative to the polls and the recency of those polls decreases until it's actually 0 on the day of the election. So in other words, not only are they saying that we have this prior of what we believe the mood looks like, and now we get this new poll, let's see now with this likelihood with our posterior, and look, that prior weight decreases in importance as we get closer to the date of the event. And so, yeah, the only thing that I wanted to add is the key value of Bayesian statistics largely is dealing with sparse amounts of information.
Yeah, I just like thinking about there are other institutions also do the forecasting, and like how would you know the 538 their model or their forecasting result will be better than other institutions?
Yeah, how do we know that theirs is going to be better than other institutions?
Yeah.
We looked at the other institutions and compared the elections. No, the main reason that we focus on 538 here is a few things. One is their popularity, frankly, among the data science community and an understanding and agreed recognition of their significance. And the second is they're so open about their methodology and their data that it's easy to give a presentation walking through how they go about things in terms of like why we think 538 objectively is valid, independent of cherry picking nice things that it makes it easy to give a conference talk about. They're objectively quite good because the amount of rigor, and to Matt's point earlier about trusting the process as much as that is a cliche about we believe. So for example, Silver is very open and will tweet throughout his electoral process about how much he thinks a new factor could or could not matter. And so roughly in March of last year, he was thinking about incorporating that local state legislature element of like how much does the state mood and the state house affect national elections, house elections, governorships, things like this. And he tweets out this massive Twitter thread where he's like, based on all my estimation and work here, this did matter quite a bit in prior elections. And then he baked that into the 2018 model with that knowledge at that point in time. And so one reason that 538 is so strong is that they lean so heavily into rigor and empiricism over perhaps saying we want to see a given result and we want to backstop our performance against that result. So much so that even I think pollsters engage in herding, where if they see that they're an outlier result, they think that their result is wrong, and they'll put their own finger on the scale to bring their result closer to what others in the district may see. So long story short, why 538 for this presentation? Openness of data, recognition of understanding, reliance on empiricism.
And also they use some micro level data.
What's that?
They also use some micro level data.
Yeah,
Just
in
the
micro,
macro.
yeah, across all levels, right? National mood, individual districts, states. It's great.
Thank you.
Yeah, I think, so the next talk starts in about 10 minutes, so.
Yeah, so they're going to kick us out. But thank you all again very much for your time and your attention.